artificial intelligence will completely transform our world. But what is AI? Why will it affect you? And how can you and your business survive and thrive through the AI revolution? Welcome to AI and You. Here is your host, author, speaker, and futurist, Peter Scott.
Hello and welcome to episode 188. My guest today is Peter Norvig, who literally wrote the book on AI. He's co-author of the standard textbook, Artificial Intelligence, A Modern Approach, used in 135 countries. The other author, Stuart Russell, was on this show in episodes 86 and 87. Peter is a Distinguished Education Fellow at Stanford's Human-Centered AI Institute and a researcher at Google. He was head of NASA Ames' Computational Sciences Division and a recipient of NASA's Exceptional Achievement Award in 2001. He's taught at the University of Southern California, Stanford University, and the University of California at Berkeley, from which he received a PhD in 1986 and the Distinguished Alumni Award in 2006. He's also the author of the world's longest palindromic sentence. Recently, he co-authored an article in Noema magazine titled Artificial General Intelligence is Already Here, arguing that today's frontier models are displaying the key property of generality that puts them within the definition of AGI. Let's get into the interview. Peter Norvig, it's a pleasure to welcome you to AI and You. And you have had a very storied career here, famous, of course, for the textbook Artificial Intelligence, A Modern Approach, which is the standard textbook used in 1,500 plus universities, I believe, for teaching artificial intelligence. And maybe you could tell us the story of just how that started, how that came about. Because in 1995, artificial intelligence did not have the prominence it does now, of course, but things had been shifting. So why don't you tell us the origin story of that?
Yeah, I think that's exactly right. I think the field was shifting about that time. I came up in the 1980s, and in the 70s and through the start of the 80s, the field was dominated by an approach called expert system. What that meant was to build an AI system, you went out and you interviewed an expert, say a grandmaster chess player or an expert in factory manufacturing or something. And then you asked them what they did and you tried to translate that into a formal language that you could put into the computer and then run that. And it was basically based on logic. If A and B and C, then do X. And it was based on self-reports of how people think about things. Starting in the late 80s and into the early 90s, there were two big changes. One was moving from pure logic to probability to sort of admit that the world's uncertain. And the second was moving from writing things down with the blood, sweat, and tears of graduate students to machine learning. I was saying, oh, we're not going to tell it what to do. We're going to show it some examples of what to do. So I was at Berkeley and the AI faculty there. You know, we had grown up. We'd used various textbooks that very well formulated the older vision of the field, but we thought that the field was changing and there wasn't really anything that did a good job of representing that. So we would go out to lunch and we would say, yeah, we should write a book. And that never happened. Then I felt like this era of big data was upon us. It was hard for me as an academic to get the resources I needed, the data, the computing power, the number of people on the team. So I went off to industry, actually to Sun Labs. And then like a year later, I met Stuart Russell at a conference. And I said, you know, how's that book we were always talking about? You guys must be halfway through it by now. And he said, nah, we talk about it now and then. We haven't done anything. And so I said, let's just do it. And so we did it. I guess we'd now call that working remotely. So I was with Sun Labs, but it was actually in their Boston office. Stuart was at Berkeley. We did it over the internet, which at that time did not mean Zoom meetings and GitHub. It meant transferring files by FTP, but we got it done. At the time, we thought this is our personal vision of the field. And so it's kind of easy to do the first edition because we just wrote what we knew. But then it became really popular and then it became a lot harder because now we said, oh, and now we're representing the entire field, not just ourselves. We better be more careful about what we say. So we've gone through 4 editions now.
And you've talked there about the transition in the field, from the expert systems, the symbolic processing, to the connectionist, network-oriented, big data, probabilistic computing, which is quite a shift. At the origin of artificial intelligence, it appeared that the leaders of that field thought that they could decompose everything that needed to be done or thought about or was worth computing into logic, no matter what it was, how big a thing it was, how complex it was, driving a car, recognizing a buffalo, making coffee. They could get that decomposed down into enough rules that it would look like a large set of subroutines calling each other. And we know now that just wasn't going to happen. But it must have been quite the shift in the field to go from that purist approach to essentially giving up and going, okay, we can get there if we throw enough data at it, but we're not going to understand exactly how that happened. What was the feeling like from someone like yourself who was at ground zero of that transition? Was there a battle? Was there a debate? Was it heated?
Yeah. So there have been multiple changes in the field of AI over the years. So I mentioned going from pure logic to probability, dealing explicitly with uncertainty. I mentioned moving to machine learning, learning from examples. And one of the important ones, I think, was moving away from this idea of strictly defined symbols or concepts. You know, the concept of dog or cat or chair or table. In the early days of AI, we thought we're just going to write down these three letters, D-O-G, and then that's going to be a concept, and then we're going to explain what it means, that it has four legs and so on. And we realized over time that that didn't work very well because these concepts don't have strict boundaries. You know, even something like a table doesn't have a strict boundary because maybe there could be a makeshift table where you throw a door over two posts, and does that become a table or not? We're not sure. So this idea that there should be absolute sort of Platonic concepts, that didn't work out very well. And that's true for these mundane types concepts, and it's even much more true for harder ones like truth or justice. How do you define that explicitly? So we realized we couldn't define them explicitly. It didn't make sense to say there's this atomic concept that stands by itself. Rather, we said, we're going to move away from that. We're going to have these things that are called embeddings, which are points in a multidimensional space. So each of these words would be represented by a point in space that has many dimensions. And now we can introduce this notion of nearness, which you never had in logic. In logic, there's no idea of near. Everything's either true or false. But in these connectionist models, you can say, this concept is similar to another concept. What we know of one might be true of another. We're not quite sure where the boundaries are of this concept because it has multiple attributes rather than just having a single atomic form. And I think that's what the main breakthrough that was responsible for the big advances we've seen in the last couple of years. So there's a lot to the entire connectionist paradigm, but I think this moving away from hard defined symbols towards vagueness and definition, I think that was the most important part of it.
I think this is opening up for me a new view on the purpose and the scope of the field of artificial intelligence, because I'm looking at what I learned in computer science, and that was based very much on formal logic, mathematics. It was an outgrowth of mathematics as I learned it. Things like databases were defined in terms of theorems. You had things like lambda calculus and predicate calculus that were the foundations of computing, and it was very mathematical. So everything is defined in terms of assertions that are true by definition. And now artificial intelligence seems to be coming from a different pole, a different end of some axis, which is rooted in wanting to deal with the real world instead and deal with very fuzzy concepts in the real world. And it's not as fuzzy as, say, coming from psychology and social sciences or something like that, where there would be a larger mismatch of the type of minds involved. But in a way, it seems as though AI was sneaking some kind of very different way of thinking about computers into the field. Does that resonate with you? Does that feel like a useful description?
I think that's right. So in one sense, I think that's exactly right. In another sense, we do still have algorithms. They're just at a different level, right? And so you were saying in traditional math, you have an algorithm, say the square root algorithm, and you can see how it computes the square root. And when you give it 9, it gives you 3. And when you give it 16, it gives you 4. So there's a part of the algorithm that's static that just does this computation, and then you can feed in any number and it gives you the right result. So in some sense, the neural nets are doing the same thing. They're doing a bunch of math. It's mostly computations over large matrices. But the point is that you can give it any kind of training data as input, and then it comes up with the system that will do the results. So in that sense, it's still an algorithm. But the interesting part is that all the exciting part is now learned by the algorithm from the training data rather than being coded in by the programmer.
But that's the interesting thing. We're using algorithms, we're using formal, rigid mathematics to create models that operate according to principles more like the human brain that is able to encompass very fuzzy things like dog, cat, and beauty. And so we're basing a network approach to understanding the world on top of formal algorithms and hardware, and the human brain operates the other way around. Like when I'm thinking about the square root of 16, I'm using a neural network to get the answer, but I've encapsulated formal mathematics on top of that. So we're getting a bit philosophical here, but when we look at how the field is evolving here, do you think that there's any kind of shift in the way that people define the scope, the breadth of artificial intelligence now from how they used to?
I think that's exactly right. Daniel Kahneman, the psychologist, talks about system 1 and system 2 thinking in people. He says system 1 is this kind of automatic thinking. You see a situation, you recognize it, and you do something in response. And system 2 is this deliberative thinking of you think out if A, then B, then C, then D, and so on. And he points out that people are better in most cases with the system 1, and it's hard to train yourself to do this more deliberate thinking. I think in computer science and AI, we traditionally went full blown for system 2, saying, of course, what computers are going to do is this deliberative step-by-step thinking. And this system 1 sort of recognizing a pattern and immediately coming up with the answer, that wasn't part of computer science. That was something else. And now this connectionist deep learning models are switching that around and saying, no, we're going to really focus on this recognizing patterns. And it's going to be hard to do this deliberate thinking. In that sense, so I think we call them neural networks. I wish we hadn't used that word, because the components of these computer models are very different than the components of a human brain, even though they do have connections to each other. But this idea of saying we're now going to try harder to do pattern recognition, and then you're going to have to build on top of that the logical reasoning, I think that is a big change. And one of the places I notice it, right? So I started out my career in the 1980s trying to do language understanding. And at the time, we operated as linguists, called ourselves computational linguists, and we kind of tried to write down rules of grammar and dictionary entries and so on. And we did it step by step. And if you could correctly handle one new paragraph a week, you felt like you were making really fast progress. And then it never converged. It never got to the point where adding the next thing was easier. It always adding the next one was harder. You made more mistakes than you added to it. So we realized that was going in the wrong direction. Now, we don't try to do that anymore. ChatGPT and all these other large language models, there are no linguists involved. All we do is feed it in lots of text and have it figure out on its own what the rules of grammar are and everything else. So that's a big difference. And one of the interesting things to me is, so there's two places in computer science where we deal with languages, one with natural languages, and second with programming languages. And these large language models are pretty good at dealing with programming languages. You'd think that it would be helpful to tell them, we know the exact syntax and semantics of this programming language. Wouldn't you like to know that if you're a computer model of that language? And the answer is no. They don't use that. They still say they're going to learn only by giving lots of examples of programs written in that language, right? And so I think it would be good as a field if we were able to say, here's two sources of information, system one and system two, you should learn from both. But currently, we can't really do that very well because we're so good at saying we can learn something just by giving it lots of examples. And we don't have sort of the knobs or the places to say, now we can tell you what's really going on under the covers, because we know that for the artificial languages that we invent, we don't know it, of course, for English and the natural languages.
I feel like one could almost go back, or if one could go back to that early era where you were trying to work out a natural language understanding from first principles and diagramming sentences and things like that, that one could have appeared as a visitor from the future and offer this Faustian bargain and say, here, I can give you a computer that can understand language, but it's not going to be able to give you an explanation of how it does it. Do you want that?
Yeah. Yeah. And, as I think of myself with many hats, but mostly I'm an engineer. So I would want a solution to the problem. I think it's interesting now the way we try to understand that. So if you think of the history of, say, chess playing programs, there's a big advance when IBM's Deep Blue beat Kasparov. And they did that by having lots of human grandmasters in chess sort of explain what they think the important things are. And then on top of that, lots of difficult computer algorithms and lots of specialized computing power, but basically built a specialized supercomputer to solve the task. And they're able to do that. Then we see AlphaZero from DeepMind saying, I'm going to play expert chess better than any human, and I'm not going to take any advice at all. I'm just going to learn completely by playing against myself and getting better and better. And it turned out that worked. And it started recommending moves that the grandmasters didn't understand. They said, here's a move. Yes, I see that that move is better than what I would have done. It's against the normal ways that we think about it. How am I to understand this? I understand that this is going to make sense for this move. What's the general principle? And so now they've rehired the chess grandmasters to look at what the computer is saying and try to put it into forms that a human chess master can understand.
So this is very interesting because for the many years in AI, the thing that was hard to do was what was easy for humans to do and vice versa. So what was easier to do with computers was the formal reasoning, the logic, the mathematics, analytics, calculus, things that humans had to be educated for years to achieve. But things like navigating the real world, recognizing objects, picking them up, putting them inside other ones, much harder. And understanding language to a useful degree, likewise. Now, at least that last one, we seem to have under our belt. But the things that do that don't have the human capability that we have of building the ability to do formal reasoning and analytical analysis on top of that. And as you were saying, we have computers that can compile a programming language, but we can't teach the large language models the way to use those languages the way that we learned it, only to work the same magic on them that they do with English and other human languages, which suggests that there's another bridge to be crossed. Do you think that we're going to cross that? Do you see evidence of us moving the direction of crossing that?
Yeah, I think that's exactly right. I think that's what the challenge is now. I guess I would debate a little bit. You said we sort of solved the language problem, and I think that's not quite right? So we've done amazing things. And you're talking about if we had time travel and you could go back to me in 1985, say, and and say, here's this chat program, look at how well it processes language, yes, I would have been totally amazed. It said, wow, this is fantastic. I didn't think we were going to get there. I remember at one point, my PhD thesis advisor, when I was complaining of, I'm trying to process this 3-paragraph long story and how hard it is, so on, and him saying, don't you want someday to do the complete works of Shakespeare? And me thinking, how could we ever get there? But now, to some extent, we have computers that process the complete works of everybody and can make up stuff on their own. So that's incredible. So I would have been completely amazed back in 1985 or whatever to see what we had today. But I would have been amazed not only at how good it is, but also at how bad it is. Because I never would have imagined that something that could be so good at so much of language processing could also make the kinds of mistakes that the systems are making now, right? I would have thought you'd be uniformly good if you were at that level. But we're not. It makes lots of silly mistakes. And some of that, I think, is, as you say, that we built these systems to kind of react to patterns. And so they're better at this immediate thinking and they're less good at reasoning step by step. But some of it, we don't really understand exactly what they've done. And I think there is a lot of work to try to get that right, to try to eliminate all these errors, to try to be able to do longer steps of reasoning. So we have machine learning, but we don't yet really have machine teachability. So right now, you show it a picture to your image processing system and it says dog, and you say, no, it's a cat. And the only thing you can do right now is say, I want you to get that right. So here's another 1,000 pictures of dogs and here's another 1,000 pictures of cats. Now you retrain yourself and hopefully you'll be better. But what you really want to say is, no, you got that one wrong. Look at the ears or look at the snout. That's really the differentiating point. And we don't have the language now to do that kind of thing. Mm-hmm. And if we did, then probably a lot of these things we could learn with far fewer examples, rather than saying we need thousands and thousands of examples, say, well, maybe you only need a couple. And we have that in some aspects. So we have this few shot and one shot training where you can go to a large language model and you can say, I want you to do this task. And sometimes it'll get it right, but sometimes it gets it wrong. So we're in this strange state where we don't quite understand what the limits are. And I think we'll get there. I think we'll be able to reintegrate this kind of reasoning on top of the neural net reasoning, but it's going to take some time.
Well, you referred to something there that is a pattern that we seem to be recapitulating over and over in AI, which is that we believe that some task could only be accomplished by a general intelligence, something that has got the capabilities of a human, that we don't understand how it would do that. But if it could do that, it would have to be generally intelligent. And then we find a way of doing it that doesn't require that. So the quote I always remember is when Deep Blue beat Kasparov and Douglas Hofstadter said, my God, I used to think that playing chess required thinking. Now I realize it doesn't. And it does, of course, require thinking for humans, but it doesn't require thinking for computers to do that. You can't have a conversation about philosophy with Deep Blue or AlphaZero, and yet they can be the best chess players in the world. And 5 years ago, I was saying I want to be the first person to say, my God, I used to think that passing the Turing test required thinking. Now I realize it doesn't. And I could say that now, but I don't think anyone seems to be caring about the Turing test any longer. That's the end of the first part of the interview, which we've split in two, as we often do, for attention span and download ease. In today's news ripped from the headlines about AI, a team of researchers at the Korean Advanced Institute of Science and Technology has developed the world's first humanoid robot airplane pilot. It looks like a bunch of robot arms sitting in the pilot's seat. The robot is called PiBot, and while there have been other robot pilots before, this is the first one that has a humanoid form factor. Project leader David Hyunchul Shim said, quote, humanoid robots do not require the modification of existing aircraft and can be applied immediately to automated flight, end quote. Because PiBot incorporates ChatGPT and can remember Jefferson charts for the whole world and the quick reference handbook of situational checklists, The researchers say that its ability to manipulate the switches of the cockpit and visually analyze the internal and external environments give it an advantage over human pilots. You're not going to see it in your plane anytime soon, though. It's only been tested in a simulator so far, and the project has until 2026 to run before they look at commercializing PyBot. Next week, we'll conclude the interview with Peter Norvig, when we'll talk about how the rise in prominence of AI in the general population has changed how he communicates about AI, his feelings about the calls for slowdown in model development, and his thinking about general intelligence in large language models and AI winters. That's next week on AI and You. Until then, remember, no matter how much computers learn how to do, it's how we come together as humans that matters.
That's all for this episode of AI and You. Please leave a rating and comment and share with your friends. Get the book Artificial Intelligence and You and see more videos and articles at aiandyou.net. That's aiandyou.net, where you can also send us your questions. Thank you for listening.